formation process, which is also very popular in manufacturing industry when you want to suppose manufacture the pipes, because the rollings they have their specific dies at the circumference. When you want to roll something, it could be a straight sheet metal working, or something like a pipe. It keeps on changing the die. So let me show you first of all slides, then I will come back to the analysis. So I would prefer you go home and read these slides when you have time. And if you don't, but try to spend some time, okay, so that you will learn. You see the hot rolling, these are the two rollers. Before I go to the next slide, I want you to open your notebook and draw this rough sketch. One roller and second roller. Now it is similar to this, okay? So let me reduce a little bit. And then the material, if you closely take a look, the material, the metal, hot metal is being squished between the rollers and is coming out of the rollers. Initial height, we call this as initial height, is different. Look, it's called here, this is my plate coming inside. This line I should make it a little bit up. From the center. Let me draw it with this way. Radius of the roller, it is very important. And initial height, we call it the back, just like H, P, and final height. So what is the change in the thickness of the plate? This is large plate. It is extended towards all the way here. And if you draw it like this, these are two rollers. Okay, I'm just showing you the sketch. It's just like this, and this is this. And this is a big roller here, and it's going over there. And this is just a sketch, but try to imagine, visualize in your head to understand the process. So there is another, this is the perpendicular drop on this line, and then this angle is important. And that angle, the delta H, we call this as change in the thickness from the initial thickness minus final thickness. And this thickness depends upon the coefficient of friction, like a forging. And remember, it's like it will be similar to like a forging process. And mu equals to the coefficient of friction, and that is very dependent. So, and the diameter of the roller, this is the diameter of it. Okay, the diameter of the roller, maximum diameter, it depends upon this formula. coefficient of friction. You see my point? So you should understand. You will do the question and verify whether mu, if I say mu maximum phi, then you will use this. And the diangle in this case, it's not actually a die, is the angle between the initial point of contact to the point of leaving. Okay, that is the angle. And how much is the angle? So the formula is change in the thickness divided by the r. R is the radius of the roller. And maximum thickness you can achieve using this formula, mu square r. Just for example, I'll give you an example before we go to the slide details. For example, I say, can you actually reduce the thickness to 0.6 millimeter? If you have mu equals to 0.1 and the roller radius equals to 75 millimeter, then you will use this formula. Can you achieve that actually? So let's use this. Open your calculators and let me know whether you get mu square r. So let me plug it in over here. Mu equals to 0.1 square 75. How much do you get? 0.75. But actually we want to reduce it to less than 0.75. So is it possible? You will say, no, professor, that's the maximum thickness which we can achieve. A maximum reduction. In the rolling process, we reduce the thickness of the metal, sheet metal. Have you understood this understanding? This is important. We are going to solve similar problems. So and then the arc length. Look, this is my arc length, which is being forged, I would say, or rolled. Roller is similar to forging. I'm going to show you in a bit why it's similar. So arc length usually S is equal to R theta, correct? So I will tell you L equals to, like, S equals to, in our case is similar to R theta, but R delta H. Please use this formula. And the P average, the average pressure equals to Y flow 1 plus mu L to thickness average. And average thickness is equal to nothing but beginning height, final height divided by 2. This is the average thickness. And I already told you mu equals coefficient of friction, L is like an arc length, and this is the specific formula for arc length, or the length under the roller's contact, the length inside. Okay, let me tell you. Look, if you tell me, look, this one is being forced, right? Look over here, this is the length being forced, and this is extended all the way. So how much is the area being rolled? It's like a rectangle. Rectangle has a thickness. This is this side times this side. We call this a width. L times W is the area, rolled area. Under the roller is that area being pressed down. You understood this point? So if you know the pressure, average pressure, can you find out the rolling force? Yes, you can find out, because force per unit area is what? Pressure. Agreed? And pressure is average pressure times area, roller area. And what is that? That is equal to length of the arc or being under the roller times the W. You understood this analysis? And in this case, what is y average flow stress yield? In this case, it is not equal to K epsilon n plus or m, but it is equal to 1.15 times this one. Because we are doing per unit depth. You remember strain distortion energy by von Mises says that the 2 tau flow, when you consider just a plane stress, equals to 1.15 times the sigma flow. But in the previous case, remember, over here, look, over here we did not say that it is 1.15. The sigma flow, average sigma flow is not equal to 1 point, because this is not a plane stress. This is a complete deformation. It's not per unit depth, something like in our forging and in our rolling. In our rolling, we assume that's per unit depth, and depth is not changing. You see, look, this our depth W is not changing at all. But in our drawing or extrusion process, everything is changing. That's why we say 2 tau flow equals to average flow stress, pulling stress, yielding stress. Sorry, pulling stress is sigma x, average flow stress is K epsilon. You understood this difference between the, why do we have, it's like a forging. We also consider the forging as per unit depth. Then we multiply with the depth, total forging force. Now another formula. So over here, so if it is cold rolling, then you will use this formula. And if it is hot rolling, cold rolling means actual temperature is less than half of the melting point. And if it is hot rolling, then you already know that. What is that? The temperature should be greater than half of the melting point of the metal being rolled. Okay, 1.15 times C epsilon dot to the power m. So you change this formula. This is sigma f times 1.5, sigma f 1 times. Okay, so another thing which you will, and you will see epsilon for this case. What is our epsilon? In this case, the strain equals to ln final divided by initial. Agreed? Remaining things are the same. But over here, strain rate in this case equals to average strain rate. I would say average strain rate equals to divide by time. And you can also assume roller speed divided by the arc length hp over h. Like roller speed equals to r omega. If I tell you the radius of the roller and the angular speed, you can find out the tangential speed. Tangential speed is the speed of the roller at the tangent, at the point where it is pulling the metal inside the roller. And this, look, here it is meters per second. Here the unit of the L, which is in distance meters, and this is dimensionless. And now it is rate, strain rate. You understood this dimension of the strain rate? So you will use this formula if it is hot rolling, and you will plug it in over here to find out sigma average flow stress, which is equal to 2 tau flow according to the Mohr stress circle. and von Mises criteria. Von Mises criteria is taken when there is per unit depth, and when it is completely deformed, like in extrusion drawing, you don't multiply by 1.15. You take it like a Tresca equals to the sigma flow. So another thing which you will also come across with this formula, that the torque equals to force times the moment arm, and force times the moment arm here is L by 2. What happens actually, we consider a neutral point here. This is my arc. This is the total arc length, L by 2. So L by 2 here, L by 2 here. So what happens actually? What happens here? This is the pulling. This is a neutral point. Here there is a neutral point. We will study it. When the metal plate comes inside the roller, initially it is pulled inside the neutral point, but after it passes the speed of and this is the front speed, then it is forward here, so it pushes back a little bit the force. So it's like a concept of the rolling process. So force per roller equals to the P average times the area being rolled. Did I tell you that formula? And area being rolled is L times W. You agree with your professor? And P average is equal to 1.15 Y flow 1 plus mu times L over 2H average. Here one more thing. If you want to see, that small rollers, if small rollers, then small reduction. But what is the threshold? How would you say it's a small roller, it's a big roller? Then there's a criteria. If H average over the arc or roller contact length, I would say roller contact length, if it is greater than 1, then we also call it as delta. If delta is greater, then it's a small roller. And what happens? What happens in this formula? Look, what happens if in this formula, if this is a small roller? Look, I'm going to change this formula. If H average over L, H average over L, if it is small, oh sorry, greater than 1, can I write down like this? If it is large in the denominator, larger the denominator, smaller the number. Agreed? Smaller the number means, can I write down just 1 plus 0? You see, for the small rollers, the second term goes to 0 almost. And then I can write down P average equals to 1 point. A very good estimation. You can finish the problem very quickly. You will see rollers problems are easier. If you do the math, easier than forging. So if you know the P average, you can find out the rolling force using this formula. Do you understand that? And what if you have large rollers? Let me tell you, if large rollers, that means delta. What was delta? H average over L. H average thickness divided by the length in contact with the rollers. Previously, it was very large, larger than 1, right? In case of small rollers. But in this case, it will be opposite to the previous assumption. That what will happen? It is very, very small, smaller than 1. And the friction force is significant for the large roller. And what will happen to P average? P average, you will consider this whole formula. Or in case of a cold forging, I would just write down sigma average flow. Do you understand how to calculate the average force for the large rollers, for the small rollers? And in case of a large rollers, friction is more because contact surface is larger, so it's almost the same. So let me tell you the last formula, then I will start the slide. Force per unit roller. So force of the roller can be found by P average times the length under the roller times the W, the width of the sheet under the rollers. This is my roller sheet here. I would say length times width. You see my point? Similarly on the other side. But then what will happen? The power of the motor, because you see it is being rolled by the motor power. Okay, you see that? What is the power? Torque times omega. You have done that before. Power equals to torque applied to the motor times the radians per second. The what is the speed, angular speed, radians per second. Okay, and then how would you find this out? So torque equals to force of the roller times the length under the roller divided by 2. The moment arm is the torque times omega. See my point, guys? And what is omega? 2 pi. If I tell you RPM of the motor, 2 pi n revolutions per second. N is in RPM. So now this is the complete formula of finding the roller force. Since I did not go through the derivation process, I just showed you some of the formulae. Based upon your previous knowledge of drawing, forging, we only need this formula based upon your previous knowledge skills. You see, based upon this one. Although this formula has been derived in our slides. Another thing I want to show you, how would you find out the maximum? Did I tell you the maximum? Yeah, I believe I told, yes. The maximum reduction can be found using this formula. And the angle, biting angle of the roller, how much is that? Delta H over R. Or look, that is also equals to alpha equals to alpha. This is also equal to alpha. Maximum biting. Okay, let me go one problem. Before I let me go over slide by slide now. Let's go over slide by the next slide. You see successive rollers. This analysis I have given to you. Now let's see the applications. You see the sheet metal is like an angle iron at 90-degree, and some of the rollers are pulling the metal and they are deforming it successively so that we should have less load on the motor. If you have how many rollers? 3, 4, 5 rollers. You keep on reducing the thickness successively. Yes. Yeah, it will pull it faster. So pulling force, the speed maybe is different than the pushing force. It comes to so. Look, it's a ring roller. So it's making a ring to the die. You see so big rollers? And some rollers have their contours, the shapes, design inside the roller like a die. So you can chamfer the uh, material being deformed. You don't need to do specific chamfering. And this is a roller machine. It's very big. One motor in the top and then one more in the bottom. Equipment. I think you can find some manufacturing companies in Georgia after you graduate. You are about to graduate after maybe 2 more semesters. This course is a upper junior level. How many of you are seniors? You see, you see, you are about to graduate in this fall or maybe the next spring. Who is gonna graduate this fall? Good luck. And the spring 2027. You see, this course is very well designed for you to lead the company. You see how many rollers? Look, a lot of rollers here. After the furnace, you see the hot metal, hot rolling. Less than melting, half of the melting point is still cold. So you will apply this knowledge. I'm gonna give you some help. If you need your some help in future, you can shoot me an email. You see, different process. I-beams even can be rolled. You see, the girders in our buildings, the steel beams can carry the load of the whole beam. These are the products. And I-beams, railroad tracks, they are being rolled. You don't need to machine the railroad tracks. It's like a forging. So big rollers, the beams come and they keep on shaping the railroad tracks. Very fast process and very efficient. You are not wasting the material. And you are forging. When you forge the material, it strain hardens. It creates more plastic deformation, more redundant work. The strength increases. A greater volume of matter is being brought by any other means. So you can achieve a large production volume in this. So please draw this diagram in your notebook. Open your notebooks and draw this diagram. Where is your notebook? I don't see. iPad? It's okay. I'm watching you. We have sufficient time to solve one problem. If not today, we can finish it on Thursday after the test. I don't want to rush. So the question was asked the speed of the metal coming out of the rollers. The final speed is larger than the initial speed, according to this formula. So the metal coming out of the roller is a little bit faster than metal going inside the roller. Okay, have you drawn it? Good job. I can see you have. And this is the analysis. It is similar to forging process. You see the pressure and the friction force, entrance and exit. As I mentioned, at the exit, the material moves faster, so it's a backward force. So that's why we have friction force on the other side. Then some derivation process. The von Mises, you see, plane strain, because we consider per unit depth. Depth is not being rolled. It remains same. Only the height is changing, the thickness. I'm coming to the slide where the final formula for your help is write down this formula. This is the height at the neutral point. Exit region. So if we have back and front tension, so the sigma, sorry, y bar, which is the material flow strength stress, so it reduces significantly if we are pulling it from the back and from the front. But still the pressure at the neutral point is the maximum pressure. The length under the contact of the roller is equals to square root r times the change in the thickness of the material. I explained this earlier. This is the derived from approximation based on the forging plane stress on misses. So this is the similar to the forging process. So please note down. I think you already have noted this down. So this is very important from here is, so I'm gonna, I think I showed you for the small rollers what is the formula changes in this case. This is equal 1.15 flow estimation, very fast estimation of the pressure and the forces. Small rollers have small friction because of the contacts, which is less as compared to the larger rollers. For the large rollers, we have this formula: zero slip neutral point. Material is pulled into the nip. Roller is moving faster than the material, and exit material is pulled back into the nip. Nip is the point where there is neutral. Uh, Nothing is like moving. Imagine the instantaneous resting point. System is in equilibrium. So the next one here. At the neutral point, the thickness is this much. And we already wrote down the torque per roller to this formula. Power per roller. Finding out certain conditions, whether it can roll certain thickness or no. Processing limits. And then the cold rolling. And the hot rolling. So we will start another problem on Tuesday, Thursday of the roll.